at the Lanthanide series. If you look at your notes, that is page 11. Page 11. So we are looking at Lanthanide series. So these are elements that are classified by filling up the anti-penultimate 4F energy level. So we are basically filling the 4F shells. Okay, so if you look at the table that you have there under physical properties, then you see that it ranges from lanthanum to lutetium, okay, with the us filling the F shells, the 4F shells, but we have 6s2 as the configuration, the outermost configuration. So kindly follow this with your notes that you already have. So the oxidation state, you see that they vary from +3 times +4, and then we also have +2, and this is because of the, like lanthanum, we have 5d1, 6s2, so it can be able to lose all the 3 electrons to give us an oxidation state of +3. Cerium has 4f1, we have 5d1, and then 6s2, and this can give us a +3 or a +4. Sorry, a +4. So they vary from one element to another. So the sum of the first 3 ionization energies of each element are very low. So it means it is very easy to lose these 3 electrons. Remembering that ionization energy is the amount of energy that you require to eject an electron from a gaseous atom. So it is a little bit easy to remove these 3 electrons. So that makes the ionic, these +3 states, to be ionic, because you can easily ionize this compound. And the Ln3+ dominates the chemistry of these elements. But if you look at Ln2+ and Ln4+ ions that do occur, they are always less stable. So less stable, or some books say unstable. Some books actually say they rarely exist. These oxidation numbers of +2 and +4, they do occur, particularly when their occurrence will result into 3 things. One, either formation of a noble gas configuration, like if we'll have selenium configuration, or if it will give us half-filled F shell. So we know what a half-filled F shell will be. 1, 2, 3, 4, 5. You add another 2 there. So they're 1 each, so those are 7 electrons. Or completely filled, that will be 14 electrons. So the 4F electron in the antipenultimate shell are very effectively shielded from their chemical environment outside the atom by the 5s and 5p electrons. So if we have that, then we know that there's a lot of shielding by the inner orbitals here of the 4F electron. The inner orbitals, that is the 5s and the 5p, they create a shield for these outer electrons here. Therefore, the 4F electrons do not take part in bonding. They are neither removed to produce ions, nor do they take part in any significant, when we talk about crystal field stabilization or complexes, in formation of complexes basically. So they do not play an active role. The octahedral splitting of the F orbitals is only about 1 kilojoules. When we talk about octahedral splitting, I'll give an example using the d orbitals. We know that there are 5, but they can be split like that by the ligands. So when the ligands have split them, then the difference between this energy, this is what we are calling the crystal field splitting or stabilization energy. So delta O will be in an octahedral field. So the difference in energy between these 2 orbitals and the 3 is what we are calling delta O, and that is the octahedral amount of energy that will be determined in an octahedral field. So whether the f orbitals are filled or empty has little effect on the normal chemical properties. However, it does affect their spectra and their magnetic properties. So they play a role in spectra, which is about color and magnetic properties, as we will see when we talk about paramagnetism. Thank you. So we have looked at that. Now we want to look at the magnetic behavior. The last time we mentioned something on paramagnetism and diamagnetism. And so we want to look at it in terms of the lanthanide series. So paramagnetism is shown by the positive ions of lanthanide except lanthanum ion, which is F0, and then the lutetium ion, which is F14. The reason why we have this paramagnetism is due to the presence of unpaired electrons in the incomplete F subshell. So you're saying that the reason why we have paramagnetism is because of unpaired electrons that we can be able to see in the F subshell. So the lanthanides basically differ from transition elements in the fact that the magnetic moment do not obey the spin-only formula. They don't just use a spin-only formula, but they use another factor, which we are calling the orbital quantum number. So when we did the mu effective, the effective magnetic moment for the d orbitals, for the d series, then we say that it is equal to mu effective is equal to the square root of n into n plus 2. Unit is Bohr magnetons. So n is a number of unpaired electrons. So this is because in case of transition elements, the orbital contribution is quenched by the electric field of the environment. But in case of the lanthanides, the 4f orbitals lie too deep to be quenched. And that is why we are saying the magnetic moment is calculated by considering the spin as well as the orbital contributions. So the mu effective for the lanthanide series then is equal to the root of 4s into s plus 1 plus L into L plus 1, and the unit is Bohr magnetons. So S is a spin quantum number, and L is the orbital quantum number. Okay, so this is one of the differences that we have when we look at the D series and the F series. So since The charge in ionic radius is very small. This is in terms of separation of the lanthanide elements. Since the charge in the ionic radius is very small, the change not charge, the chemical properties are quite similar. We saw that the difference is very, very small in terms of picometers. This makes the separation of the element in pure state difficult. And so separation is done by ion exchange methods, which is based on the ionic size. So it's very hard to separate them using other physical methods, but you can be able to use ion exchange methods to separate them because of the small ionic sizes. And finally, we come to the colors. We come to color. And we are saying that the lanthanides are silvery white metals. However, most of the trivalent metal ions are colored, both in the solid state and in aqueous solution. This is due to the partly filled f orbitals, which permit the FF transitions. Just like in the d orbitals, this one also has the FF transition. When we talk of FF transition, I will give an example of the DD transition. We said normally the 5 should be in the same level, degenerate, but they can be split like that. And so once they're split and there's some electrons here, there can be movement of electrons from these d orbitals to this one. So this transition between the d orbitals is what we are calling, is what creates color. Because as they move, then there's emission of some radiation that can be able to be seen in the visible region of the electromagnetic spectrum. So that transition is what we are calling DD transition. So for the F, there's also FF transition when there's movement of electrons between the split F orbitals. So this only happens when they are partly filled, because when they're completely filled, then you don't expect to have any form of movement of electrons. So lanthanide ions with XF electrons have similar color to those with 14 minus XF electrons. So if you compare the two, those that have X electrons in the F, then you compare with them by subtracting 14 minus X, then you see that they have similar colors. And this is because their transition will be basically the same. So I'll want you to kindly go through this in relation to your notes and see if you understand this introductory part of the lanthanide series. Thank you.